Bismillahirrahmanirrahim. Assalamu alaikum dear students. I'm Dr. Tahir, as you have already introduction about me. I'm going to start with my first lecture and on the topic that is one-pot synthesis. I've already shared a few notes with you through WhatsApp, and I've given you a few relevant question in your recent assignment. Today I will explain why such reactions are called one pot, what is one pot strategy. They are the reactions which come under the main heading, that is green reactions. Sometimes they are also referred as eco-friendly reactions. Why they are called eco-friendly, why they are called green reaction, and why they are called one-pot reaction. I will explain all these terminologies with suitable examples for you guys. And the examples I will take will be from the basic concept which I've given you during my last lectures in your university courses. Like we will be using simple reductions, oxidations, nitrations, reactions with aldehyde, reactions with ketones, and then I will relate those reactions with one-pot synthesis. At the end, one-pot reactions cannot be applied to all sort of reactions. Why some reactions could be one-pot, why some other reactions can't be one-pot. What are the advantages? What are the limitations of the one-pot reactions? I will explain to you all. I've previously shared one PDF file, one of the very eminent professor, which reviewed the usage of certain synthesis of certain drug molecules using one-pot reactions. So, in fact, one-pot reactions could be used for the synthesis of a number of type of molecules. They could be drug molecules, they could be synthetic dyes, they could be complexes, or many other type of compounds. What will be the basic criteria for a reaction to be regarded as a one-pot? I will explain to you. I will be using whiteboard along to explain a few relevant examples for all of you guys. Please stay tuned. So now I'm to explain with few very relevant examples which are very much known to you guys. Let me start with very few known examples which we have already discussed with you guys in our classrooms. If you are going to do the nitration of benzene, you take benzene, you put in HNO3, you put in H2SO4, and you need some, let's say, for some other reaction you need some solvents. You produce nitrobenzene, very much known reaction for you guys. Then you may go for reduction. Maybe in another reaction. Let's say you've done one reaction. This is your product. Product number 1. You have started with benzene. Nitration has been done. You got nitrobenzene. This reaction has been done in a one flask. You may say that the reaction has been done in one flask. So you have a nitrobenzene over here. You purify it as we do in case of any product. We purify them. So you purify nitrobenzene. Then after purification, this nitrobenzene becomes again your reactant. the product of the first step, first reaction, now it has become a reactant for any other reaction. Now you bring in conditions, reagents that is required for reduction. Once you go for reduction, you get aniline. Let's say it's a vessel number 2 where you put in nitrobenzene along with reducing agents, and then your product over here is a sort of an aniline. You purify again. You purify that. Step number 2, you purify that. Next, the prepared aniline which you received in the reaction number 2, I may call it as reaction number 1, then I may call it as a reaction number 2, then I can call it as a reaction number 3, where let's say you have an aniline, you react it with a sort of an aldehyde, it could be a benzaldehyde. We have an idea how the reaction happens. You need sort of acids, you may have any sort of solvents as well. As a product, we have ideas. We produce amines. Amines you purify this one as well. So if we look back again, we started from benzene, we performed nitration. The first product was supposed to be the nitrobenzene. The reaction was done in a flask as we do. We purify that product. The product of the first reaction will be the starting point of the reaction number 2. We bring in reducing agents. We take another flask, put in the nitrobenzene, put in reducing agents, and we produce aniline. And that's going to be the product number 2. We purify that. Again, reaction number 3, what we do over here, let's say we are to react it with any sort of carbonyl compound, any sort of an aldehyde. We bring in benzaldehyde, a known and easily available compound. They two react with each other to produce this aniline. So this we purify that. That's a product. We can move on again, but I'm just want to restrict to you guys over here. So this is your product. So starting from benzene, you reached amine. The reaction has gone through 3 different steps. Each step requires its own catalyst, like H2SO4 in the presence of HNO3 needs H2SO4. Over here you need reductions, you need some sort of catalyst. Over here you need like some acids as well for the reactions to complete. So at each and every step you need reagents, you need solvents especially. Each and every step you need to purify your products. These reactions are not one-pot reactions. Why? Because each step, starting from over to here, you have done it. You have used at least three vessels. In case of chemistry, the vessels are supposed to be the flasks. The pot is supposed to be a flask. So means you are using 3 flasks. Usage of flask is not a matter. It's not an issue. What is the issue over here? Each step you need to purify the product. Whatever is the side product, whatever is the solvent, that will be removed during the purification process. Removal of the byproducts, removal of the solvent means those will enter into the environment. Over here again, you are purifying your product, the byproducts, unreacted materials, and the solvents. They are going to enter into the environment. Again at the third step. If someone does so, if someone handles them in a way that he or she starts from benzene and goes to amines in a single step, he uses only one vessel, one pot, performs nitration of benzene and do not purify that, keeping the nitrobenzene inside, putting the reducing agent in, generating aniline again. Again, no purification. The aniline and the other contaminants are inside the flask, inside the vessel. You put in the reducing, let's say benzaldehyde in the same flask. It could produce the required amine. So 3 steps could be managed in a single flask without purifying these individual compounds. Such compounds are such reactions are supposed to be one pot reactions. In organic synthesis, they are called one pot. Synthetic reactions, one pot synthesis. Now let me explain it to you in a way showing you that these reactions are one pot reactions. So you can understand by looking into this a very simple reaction which we have already discussed quite a many times in your class. Let's say as I told you, you starting with benzene, you put in HNO3, you put in H2SO4, and you convert that into nitrobenzene. Over here, if into the flask again, we add in benzene, then we add in HNO3, we put in H2SO4, provide the required reaction conditions, temperature to the vessel. After the required number of hours, the nitration of benzene would have happened, giving you the nitrobenzene, this one. So at that time, what you do, when the benzene has been converted into nitrobenzene, we got the idea. The benzene has been converted to nitrobenzene. Now you can put in reducing agent because the nitrobenzene is still there. So we are not putting anything else now. We are putting in reducing agent. We are putting in reducing agent. What the reducing agent will do? It will reduce nitrobenzene into aniline, aminobenzene. It will be in the same flask. Now again, the contaminants are there. The leftover of the reducing agent, maybe a little bit of nitrobenzene is there. But we don't go for the purification of aniline. We suppose that aniline isn't there, some contamination is there, that's okay, fine. And then the vessel which carries aniline, what we do then, we put in our next reactant into the same flask, that is benzaldehyde. We put that into the same flask where aniline is already inside the flask. They will react with each other, we have an idea. Then finally they produce sort of means that is supposed to be inside this flask. If we are interested in this product, we can stop at this level. After 2-3 steps, we have this product. Again, it has a sort of a solvent inside the flask, some contaminants over there. At this time, we will purify it now. Why? Because it's going to be the last product if we are interested in it. If we want to do some reactions over here again, or we want to do some reactions at these benzenes again, then we don't need to purify again. We can keep them in the flask. Let's say this is in the flask without purification. We are again putting in HNO3, H2SO4, means we are going to do nitration again. If I'm using 1 mole, so one of the NO2 positive will attack one of the benzene. According to this group, that NO2 could be on meta position. If I'm using 2 moles, then it could be on the same benzene, or it could be on the opposite benzenes, like this way. If we want to stop here, we could stop at this point of time and purify this. If we don't want to stop here, don't want to purify that one, our interest is something else. Let's say the next step could be this product is the inside. We can put in again reducing agent. This reducing agent will reduce, if you have an idea, you will get the amines over here. Okay, if this is the product, if we want to keep it, want to obtain it as a product, we can stop at this point of time again. Again, if we want to do some other reactions at these points around benzenes at this double bond, we can move on in the single same flask. Under that condition, under that scenario, these reactions will be called as one pot reactions. Pot, vessel, in chemistry, that pot is supposed to be a beaker. For reactions, we usually use flask, so they are supposed to be one flask reaction, or more appropriately, one pot reactions. Why we perform one pot reactions? As I've told you in the beginning, these reactions are considered as green reactions. Secondly, they are also termed as eco-friendly reactions. The first example, where the reaction was done individually in one step, each and every step you need to purify them. You need to throw away the contaminations, the byproducts, the solvents, you need to throw them away into the drain, means they are not eco-friendly. Secondly, they are non-economical, because in each step you need to put in solvents, catalysts, this and that. In one pot, you have the same vessel. You're not taking out any solvent out. You're not purifying. If you're not purifying, then you're not throwing away anything. You're keeping in and then putting on the next reagent, putting in the next reactant, putting in the next reactant. You wait until the reaction completes, then you move on. How you will come to know the reaction has completed? Let's say, if you're starting with benzene, you perform with the nitration of the benzene the first step. How you know that this body has been converted into this one? There are various techniques which could give you clue. The reactants has been consumed, product has been formed. You could do that by simple TLC. You could go for chromatography like GC. You could use HPLC. You could go for NMR. I will explain these techniques, which are in fact reaction monitoring techniques. I can explain those in a separate lecture for you guys. At the moment, what I'm trying to convey is the one-pot reactions. So what I'm thinking now, you would have got multi-step reactions, a reaction which is supposed to undergo in multi-steps, like nitration, reduction, and then reaction with benzaldehyde. 3 steps, 3 reactions, individually in 3 flasks. You need reagents, you need solvents, so they are not the one pot. However, if you perform first reaction nitration and keeping the nitrobenzene, you put in reducing agent, then you bring in your benzaldehyde, then you can perform the other. Then this reaction will become as a one pot reaction. How it has become an eco-friendly, you've got the ideas, because it will not produce that much of hazardous material at each and every step. You have reduced the step. In fact, you have reduced the steps, because individual reactions require at least 2 to 3 steps. As I explained to you guys, if you are using single vessel, you are not purifying, so means you are reducing the steps. You are actually waiting for the nitration to complete, then you put in the reagents required for reduction. Then you put those in, the new reaction will happen on nitrobenzene, the reduction will happen. Let's say it takes 2 hours, 3 or 4 hours. After the completion, you will guess the reactant has been converted into the product. The product is informed, mean an aminobenzene and aniline has been formed. Then again, you will put in your benzaldehyde. You need to keep the sequence in a correct, proper way. Let's say if you're starting with benzene and putting in benzaldehyde, there won't be a sort of a reaction over there. If you take the benzene and then put in a sort of reducing agent first before the nitration, then you won't going to get your proper products. So you need to follow the proper procedures, and then you need to wait for the completion of each and every step. Such reactions are called one-pot reactions. Now I can give you another example so we can comprehend in a better way. Now I can start with another example. Let's say again, as you know, it's a basics to make you keep it familiar with basic reactions. You start with benzene, you have this sort of a compound using AlCl3. The benzene is supposed to undergo acylation. The product is supposed to be the benzophenone. I would call it the reaction number 1. Reaction 1 again. Yes, a flask has been used where initially you put in benzene. You put in benzene first, and then you add your acid halide. You put in AlCl3 as a catalyst. We have an idea about what the function of the AlCl3 is. You may get the info about this reaction in another separate video, which I will upload. So reaction happens, this product is formed, and I've told you the product will be there as a benzophenone inside the flask is there. Again, if this is the only requirement, the product, we will go for the purification. The contaminations will be removed. Let's say some solvent has been used. Let's say some sort of usually for the organic reactions, we use organic solvents. Let's say dichloromethane that has been used for this reaction. So dichloromethane would be there. At the end of the reaction, in order to achieve the product, we will need to remove the solvent. We need to evaporate the solvent. We need to remove it by any other means. We can use solvent extraction method, simple heating and removal by the rotavap. So this is your product. Let's say this benzophenone. use it and react it with Grignard's reagent. You have better ideas about this one. Over these, we react in this one. The reaction requires the presence of a little amount of acid and water, ionic ions. What happens then? The product is supposed to be something like that. Alcohol is supposed to be there. All the reaction has been done. This reaction has been done again in another flask, where what was the initial, the product of the first reaction became the reactant of the reaction number 2. So we put in benzophenol into the flask, and then we put in the Grignard reagent. We put in some sort of solvent. Let's see if I can write the DCM again. I just want to make you learn about the usage of the solvents. Why sometimes they can't be the one part, why most of the time they can't be the one parts, and sometimes they can be the one parts. So we put in this one, keeping, like say you have a dichloromethane inside the vessel, you put in benzophenone, and then you put in your reagent that is supposed to be CH3MgBr. They both react, and this product is supposed to be inside here. We go for its purification. So we purify them to receive this one. Again at this step, contamination will be removed. The solvent, it has to be removed. So at both steps, the solvent has been removed. Removal of the solvent means it would have been thrown into the sink. It has been drained out. Means it's going to destroy the nature, the environment. It's going to be hazardous for the environment, So this is the reaction. If somebody comes up and perform this reaction in a single vessel, let's say we start off with benzene, we put in benzene, we bring that an acid halide and then AlCl3. The reaction is performed inside the flask using dichloromethane as the reaction media. The product is formed. How we came to know? As I told you, there are certain techniques which confirms the formation of the product. So when the product is formed, you remove the solvent if the reaction is going to be single step. If we are going to make it a one pot, we will not remove DCM. We will keep the DCM, we will keep these bodies inside. The product is in. We will not remove it. Simply what we will do, when it has been formed, that they have been disappeared because the product is formed, then at this time we can put in CH3MgBr. When we are going to put this body in, we will be putting in when we have an idea that benzophenone has been formed, then we will put this in. If we are not sure, if we haven't got any clue this benzophenone has not been formed, then we will not put this one in, because we need to follow sequence. If this ketone hasn't been generated, then how it can react with ketone? So you need to wait first until ketone is produced, then you can react them with the Grignard's reagents. Then, as a result of the reaction, we do expect the product is supposed to be some sort of an alcohol. So as the both steps, the step number 1 where benzophenone was generated, the solvent was dichloromethane. The same solvent could support the reaction number 2 as well. the reaction of the product with the another reagent to give you the product, this product. As in both cases, the dichloromethane, the solvent is the same. Such two-step reactions can be combined in a one pot, because in both of the cases the solvent is the same. The solvent similarity, the solvent requirement, if they are same, such reactions have a high expectancy to become the one pot reaction. Sometimes it happens the first reaction requires some sort of a non-polar organic reaction, like the DCM is over there, and the next step requires some sort of a product polar solvent. So if it's a non-polar, the next requires a polar solvent. Then such reactions can't be combined because their requirements are opposite to each other. So that's why every reaction cannot be one pot. But in organic reactions, most of the organic solvents have the similar some sort of polarities. If the polarity difference is not that much, such steps can be combined together, reducing the number of steps, reducing the purification steps. So you can make the reaction to happen in a single flask. This product, this could be reacted further. Let's say you can go for the nitration reductions, reactions of alcohols, this and that. You can do the same in the same flask. What sort of? If the requirement of the solvent is the same. If the solvent requirement is going to be the different, then it will be difficult to deal in the same flask. So this is how all reactions can't be the one pot, but those reactions whose solvent requirement, catalyst requirement, or reaction conditions are not that harsh, they can be combined to reduce the number of steps, to avoid the usage of the organic solvents, in order further to avoid the I would say removal wastage of the solvents into the environment at each and every step. So this could be avoided actually in case of one pot reaction. Now you would have got better idea about the one pot reactions. They are the reactions which we apply in organic synthesis under the umbrella of the green reactions. Now you would have got the why they are green, because the number of steps has been reduced, the requirement of the solvent has been reduced, so they will be greener. Eco-friendly, because the number of steps has been reduced, the requirement of solvent has been reduced, the removal of the solvent would be reduced as well. So under such condition they could be greener, they could be eco-friendly, and they could be economical as well. Why they are economical? Because the solvent's requirement has been reduced. Let's say you are using dichloromethane 2 times for one step and then the second step. If 200 ml of dichloromethane costs you, let's say 200 rupee, then you need to use your 200 rupee 2 times, one for the first reaction and the 200 rupee for the step number 2. If you combine the 2 steps, you will have to use dichloromethane only for 1 time. So you are reducing the usage of solvent to 50% less use of the solvents. So means you are making the reaction economical as well. So nowadays in chemistry, the atom economy, economical reactions, eco-friendliness, green reactions, that is the need of the hour. We have an idea at the moment. The pollution related issues, the global warming issues, they have compelled the researchers, especially the chemists, to design such reactions which require less number of chemicals, less number of pollutants, less number of hazardous materials, They could be done by reducing the reactants, or they could be done by reducing the number of steps involved for the synthesis of certain molecules. So this is how the one-pot reactions are valuable in many aspects. As I've told you, 2-3 steps, you are getting one product. This product can be a drug molecule, let's say. Sometimes you are synthesizing a drug. A drug molecule is synthesized, let's say, in 6, 7, 8 steps. If you perform those steps in a single vessel, you reduce the usage of the solvents, reduce the number of steps. So you are designing such drug synthesis, which is one pot, which is an economical. Similarly, sometimes you can generate certain molecules which carry conjugations. Benzenes, double single bond. Such molecules are very important for the textile industry. They could be the dyes, they could be the colorants, organic molecules, they could be the dyes, could be the colorants. Like I've given you an example of an imine initially. As we have an idea, it carries conjugation in it. So it can be a dye molecule. Similarly, such molecules which can be generated in one pod, one vessel, they can be product of valuable product in some other ways. They can be usable in LEDs. They could be usable in certain other complex formations, this and that. This is how the one pot reaction that's supposed to be very important in modern chemistry, where demand is to design and synthesize the molecule in minimum number of steps with minimum number of solvents, with minimum number of chemical requirements, just to ensure the safety of the environment and also making them economical as well. So this is how I've explained a bit to you, taking the examples from the basic course which you've already read, just trying to convey what the one pot reactions are. I have an idea. I've given you one PDF notes of a very eminent professor who used these sort of reactions, one pot reactions, to prepare very complex drug molecules. And I've heard a few complaints from the students that those molecules are of complex nature, we can't understand their reaction patterns and this and that. So this is why I try to bring few examples from the basic chemistry of the benzenes, reactions of the benzenes, which we have gone through already with me in your classes, so you can understand what they really are, one pot reactions. Now I request you again, please, to again go through that PDF file which I sent to you quite a while ago, that is about the one pot synthesis reaction. Look into those complex molecules again. Whatever the length of the molecule, whatever the complexity of the molecule is shown to you, don't get afraid of those. Try to find the functionality, the functional group which are going to react. What are the reactive centers in the molecule? How they react? Is there a benzene ring in the whole molecule? Then you can have idea, okay, those benzene could undergo substitution, electrophilic substitution. If the molecule carries any carbonyl functionality, then you can imagine, okay, some nucleophile can attack on the carbonyl functionality. It can undergo nucleophilic addition reactions. Similarly, if it's a double bond is there, it's a triple bond is there, you can imagine what sort of the reaction is going to happen. Whatever the length and the size of the molecule is be, don't get afraid of those really. So I request you now again to go through that PDF file again and try to look into those examples again, and then find out the value and worth of the one-port reaction for the synthesis of complex reactions. Even then, if you can't understand those, no problems. You can keep the idea of the one-pot reactions in your mind, as I've told you, and bring your own examples. These examples never don't fit to one pot always, but at this point of time, with your level of your mind, you can fit just sequence-wise reaction and then show them, okay, we can do them in single flash. This could be the product, this was the starting, and this could be the product. I can agree with you. There are many other limiting factors that every reaction cannot be one pot. One of the factors I've told you, one step, and the step number 2, if they require solvents on opposite nature, then definitely they're not going to be the one-pot reactions. One-pot reactions are those reactions where most of the steps do require some sort of a solvent at least. Then catalysts should not be of that opposite nature. I will explain those in the next lecture. Today I'm just trying to convey what are the one-pot reactions. Please try to grasp the basic concept. Bring your own examples from the basic chemistry. Then in the next lecture, I will try to explain again that why all reactions can't be the one pot, why few are one pot, what are the limitations, why all are not one pot. So at the moment you need to know what are the one pot. Then next we will explain why all are not one pot. Hope I've tried my best to make you guys convincing about the generality of the one pot reactions as far as the eco-friendliness is concerned, as far as they are the green reactions, as far as the simplicity is concerned. They are simple because you're not doing purification. However, they're not that simple in a way, because when you are going to analyze them after each step, using any chromatographic, any other technique, then to figure out whether the reactant has been consumed of the first step, and then you need to move to the second step. That would be easy or not. You need to understand how those techniques could confirm whether the reaction has been completed or not. I will deliver another lecture on how we can monitor the progress of the reaction, how we can have an idea that a benzene has got reacted with this one to produce this one. How we came to know that. That can be done. So easy techniques are around. People can done that. People do actually. So you could do as well. We'll learn in some other during some other lecture. So again, thank you very much. Please follow my lectures on my YouTube channel. That's Chem Hub, and it's a sort of a first lecture. I would appreciate your criticism, your suggestions for the improvement as well. I'm improving my setup as well, and I'm improving my preparation as well, just to deal with you guys. So thank you very much. Please stay tuned.